go over the roadmap and especially the first problem on the assignment 3. Okay, so assignment 1 was you're given the problem. The instance is a Turing machine M, and with input alphabet sigma equals 0, 1. Question is does there exist a string x star such that m accepts x and x has the form 0 and 1 to the n for some. Okay, so that's the form of the question. Now, the important thing to realize is that here's your given, a TMN. So L is equal to the set of M. Now, once you do that right away, that's your instance, M before the colon, then you're not going to fall into the confusion of thinking the language is 0 to the n, 1 to the n. I haven't heard of my TAs how many made that error. Okay, so set of M, and then there's predicate. And there are various ways you could formalize it. It was okay to just turn the question into a statement and say there exists a string x such that m accepts x, and x has the form 0 to the n, 1 to the n. But a little bit snappier way to do it would be to say that L of n intersects at 0 to the n, 1 to the n. Okay. N greater or equal to 1 is not n. Okay. So, nice thing to review is that saying that a language includes at least one of something is the same as the language intersects the set of somethings being non-empty. So that was the formalization, and now we want to prove this is undecidable. Okay. So we want to prove undecidable by reduction from ATM4 K. Okay, now the answer key shows the reduction from ATM. I'm actually going to show the reduction from K just to be stylistically a little different. Okay, so suppose we're reducing from K. So remember what K is. K is equal to the set of M, such that M does accept its own code. Okay. So now we need to make a mapping reduction. So now, incidentally, when you have a mapping reduction, the language L becomes the target. And just as a mental help, you could change the dummy symbol in the target. So this could be L of n, and L is the language of n prime, so the language of n prime intersects 0 to the n, 1 to the n is non-empty. Okay. Now this mentally helps us because now what we see, so we need to take M and map it to an n prime such that now even when you're doing these goal-oriented things, it can even help you to sort of write on both sides of the paper. So what do we need? We need n is in K, if and only if, and over here, write n prime in F. Okay. And in some of these problems, you can do the if and only if in one swoop. But it's actually a good idea, even further, to break it up and say M and K implies, you're going to get M prime, and M not in K implies, you might get M not in K. So, working in a goal-oriented fashion, this is what you want, what shows you what you need to do as you build the code of the M prime. Now, another thing, by the way, that's okay is I'm not really bothering here with the notation for the code of the machine, but I can put it in. This makes it clear now that I am talking about codes of the machine, and in fact I referenced it there, so it's probably a good idea. The angle brackets means the code. But when you're doing this logic down here, do I care if you take time to write these angle brackets? Kind of not, but okay, I put them in. Okay, so now it's really clear we're talking about the codes of these machines. Okay, now, so now thinking of it as a toolkit again, we have our M, we're talking about K. So somewhere in the code, we're going to have a little routine where we're going to be simulating M on N. Okay. Another thing you can write is, so if we can make the language of M prime be the empty set, okay, then we're going to have that the code of M prime does not belong to this L, because it's going to fail the conclusion of having a non-empty intersection. Now, so let's see now. So that gets the idea that maybe all we need to do with this is use this as a filter. So I'll say if and when, okay, then we'll go on. Okay. So this is, okay, so if and when it accepts, then we go on. Now, what we've done here is we've already brought about, by using this as a switch, we've already brought about the fact that if M does not accept its own code, then the machine does not go on. So we can already fill in this part of the analysis, and it's for all x. M prime of x does not go on. And we can therefore already say that M prime, L of M prime is going to be the empty set because its computation is going to get stuck there. M didn't accept its own code. So we completed this part of the analysis. So last thing we need to do is here is put in a test. Is x of the form 0 to the n, 1 to the n, now, we can put this inside a solid diamond because the language 0 to the n, 1 to the n is decidable. Okay. That's where we're finally getting to something involving that language. And then, if no, we'll reject. If yes, then finally we'll accept. Okay. there's the code of n prime. So the whole thing is, yeah.
If you just accept this, the next one states, so the language of m prime became sigma star, would that also not give us our own?
Well, oh, that's true. You're right. I could. That's true. You're right. I'm in fact involving a little bit of overkill. So he's got a good point here. If I just wrote go on and accept, so this means, so let me just write in the thing though. This means for every x, n prime on input x goes on implies, okay. And now, if I just made go on be accept, then I would have the literal all or nothing switch. This is actually a good point. I didn't even think of this in my answer sheet. So you could actually almost treat the 0 to the n, 1 to the n feature as a red herring. So I could, if I had gotten rid of this part of the machine, and let's see, I had pencil actually, but okay. So if I had just this part of the machine, and it went right to accept right away, then what I would write here would be L of m prime equals sigma star. And then sigma star intersect that language is certainly non-empty, and that would imply that the code of m prime belongs to that. Okay. So that's a wonderful point. And this is, by the way, indicative that if you really internalize these ideas, you can often reuse them. Okay? Now, mind you, if the question had a predicate that forbid the language from being sigma star, then you would have to do something else. Okay. But he has a good point. I didn't think of this because I had in my mind that I also wanted simultaneously to cover the proof of regular TM being undecidable in the text, which I had skipped in lectures. But okay, let's look at the code that we literally have. So what this means is that for every x, n prime accepts x, if and only if. Well, let me finally give this thing a name. Let me call it A, x and A. So this now implies that L of m prime equals A. So now what we've got is we've got a switch between, in case the original machine doesn't accept its own code, we get the empty language. And if it does accept its own code, then we get language A. So in fact, the all or nothing switch can be tailored to become an A or nothing switch for any language A that you care to have. And also in point of fact, if you had misread the any in the original problem as saying that is the language equal to A, then this A or nothing switch would serve you to solve that also. Okay. Now I'm going to keep this. I'm going to keep this as my answer because it was more reusable for question B. So I'll just grab the language here. And now for part B, we have L prime equals the set of n, and I'll write m double prime such that L of m double prime equals L of m double prime reversed. Okay, so undecidable. Okay. Now we really do want what we have on the page, because the important fact is that K, when anyone reduces to L prime by exactly the same construction with, say by exactly the same reduction, with analysis. So now code of n and k implies dot 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 implies that L of M prime, I'll say, yeah, I'll write this as L of M prime equals set 0 to the n, 1 to the n, okay, which is not equal to its reversal. So, one thing we actually got, we're actually going to get a reduction to the complement at this. So we got not equal to its reversal. Okay. So in fact, maybe I want to define all this. I defined the language this way. So this is going to imply that the code of M prime is not in L prime, i.e. it's in complement. So strings of the form 0 to the n, 1 to the n, where n is not 0, are certainly different from their reversals, and none of those reverse strings are present anywhere in the language. Whereas M not in K implies that L of M prime equals empty set, and this implies that the code of M prime is in L bar, since empty set reversed equals the empty set. I just want to finish. Okay, so actually what we got here is that K in any one reduces to the complement of L prime. But that's actually good enough to show that L prime is undecidable. And the reason finally is that a language is undecidable if and only if its complement is undecidable. So that was, so the answer is you only had to change the analysis and note this. Okay. Finish the thing. Therefore, L prime complement is undecidable. Therefore, L prime. Okay. All right, any question about that? Nancy, I made a few more remarks about, so the one thing that I will add to this is that this language is computably enumerable. Okay. Did I ask that in the homework? Oh yes, I did. Yes. Is this language computably enumerable? All right, so now, so let me repeat. Okay. So last thing I need to ask is this language computably enumerable? And there's a heuristic guide to the answer. The answer is yes. A language is computably enumerable if you can define it with positive sounding stuff. Namely, do there exist things? Or more exactly, I should say, if you can define it in a way that anything open-ended is stated positive. So in the definition, I wrote, does there exist a string X? There are infinitely many possible strings, so that's open-ended. But does it exist? Such that M accepts X, and X has the form 0 to the n, 1 to the n. That's the 0 to the n, 1 to the n part is decidable, so it doesn't matter. It's the existence part. So I'll finally say that L is CE. Okay. Now, how could we design a recognizer for it? what we would do, so this is an idea that's worth having in your head. We could make what we call a master loop. Okay. So the master loop runs t, a time limit, to be 0, 1, 2, 3, 4, 5, off to infinity. And when you have t for a given value, what you do is you run all the strings of length up to t for t up to t steps each. Okay, so you're doing a big trove of strings. And if and when you accept a string, and that string belongs to